Hello student, I am Om Prakash, Faculty of Chemistry. In this class I am going to discuss about the dissociation and dissociation constant of weak base. Like weak acid, weak base also dissociate in the aqueous solution. The extent of dissociation is again very low, and we can calculate the dissociation constant value or the degree of dissociation of the weak base and the concentration of the OH minus ion in the solution as well as the concentration of cation in the aqueous solution. Let us take an example of the weak base like ammonia. Ammonia when dissolved in aqueous solution, ammonia when dissolved in water, it gives NH4 positive ion and the OH minus. It is aqueous since H2 is taken in excess quantity, that's why it can be written as liquid. Again, if the concentration of the ammonia in the solution is C, the initial concentration of the ammonium ion and the concentration of hydroxyl ion in the aqueous solution is 0, 0. This is the initial concentration. If the degree of dissociation or degree of ionization of this weak base ammonia is alpha, then it dissociate or it ionize C alpha, and it gives the concentration of ammonium ion is C alpha, and the OH minus ion concentration produced at equilibrium is C alpha. At equilibrium, the concentration of each species in the solution is C minus C alpha, which is also equal to C1 minus alpha, and the concentration of ammonium ion is C alpha, hydroxyl ion is C alpha. The expression of this dissociation equilibrium is Kb. B for base, Kb is the dissociation and ionization constant of the weak base, and the expression is ammonium ion concentration multiply the concentration of hydroxyl ion upon the concentration of ammonia at equilibrium. The concentration of ammonium ion at equilibrium is C alpha. The hydroxyl ion concentration is C alpha, and the concentration of ammonia is C1 minus alpha. Now the C cancel out. Now the expression of Kb for this dissociation equilibria is C alpha square upon 1 minus alpha. Again, this is a very weak base. The degree of dissociation is very small as compared to 1. That's why we take assumption here that the 1 minus alpha is approximately equal to 1. And by taking this assumption, now Kb is equal to C alpha square. Kb is equal to C alpha square. This is the dissociation constant expression for the weak base, for the monoacidic weak base. And from this equation, we can calculate the degree of dissociation of this weak base as well as the concentration of the species present at the equilibrium. Like the concentration of ammonium ion in this solution is equal to the concentration of hydroxyl ion at equilibrium, and which is equal to the C alpha. And we can also write the NH4 ion concentration is equal to OH minus ion concentration is equal to C alpha, and alpha can also be written as Kb upon C, under root Kb upon C, and this expression is also written as Kb multiply C under root. And from this equation we can calculate the concentration of hydroxyl ion as well as the concentration of ammonium ion in this aqueous solution of weak monoacidic base. Now here the Ostwald dilution law, I can also explain the Ostwald dilution law. Ostwald dilution law, and this Ostwald dilution law explains the extent of dissociation for a weak base or a weak acid. Just like for a weak monoacidic base, the degree of dissociation can be written as under root Kb upon C. C is the concentration, which is number of moles upon the volume of solution in liter, and it can also be written as Kb upon concentration is number of moles and the volume, number of moles upon the volume. If 1 mole of electrolyte, 1 mole of weak base is taken in a solution for 1 mole of electrolyte, the N is equal to 1 and the alpha can be written as under root Kb multiplied V. V is the volume of solution in liter. Now we can explain the Westphal dilution law from this equation. The alpha, the degree of dissociation, the extent of dissociation is directly proportional to the square root of volume of solution containing 1 mole of electrolyte. Like we can also say, if the dilution increases, if the solution diluted, then the degree of dissociation, the extent of dissociation increases. In this class, I am going to discuss about the common ion effect of the weak electrolytes. Common ion effect, actually it explains the degree of dissociation, extent of dissociation of a weak electrolyte in the presence of a strong electrolyte which produces the common ion, the same ion. Like as for example, in acetic acid solution, aqueous solution of acetic acid dissociated as acetate ion and H plus ion. It gives acetate ion and H plus ion in the aqueous solution. If any strong electrolyte containing acetate ion or H plus ion is added in the solution, if any strong electrolyte containing either acetate ion or H plus ion added in the solution, to keep the Ka constant, the dissociation constant, the equilibrium must shift towards the backward direction. That is, if sodium acetate is added in the solution, if sodium acetate, which is a strong electrolyte, if sodium acetate, which is a strong electrolyte, dissociate completely in the aqueous solution, if sodium acetate is added in the aqueous solution, the concentration of acetate ion increases, and to keep the constant value of the K, the equilibrium must shift towards the backward direction and to decrease the concentration of the H plus ion. We can also say, if the equilibrium shifted towards backward direction, the degree of dissociation of this weak acid, this acetic acid, decreases when sodium acetate is added in the solution, or if HCl is added in the solution, which gives the H plus ion. HCl is also a strong electrolyte. It gives H plus and Cl minus. H plus is the common ion in this case. When HCl is added in this solution, again to keep constant value of the dissociation constant of the acetic acid, again the equilibrium must shift towards the backward direction, and if the equilibrium shifted towards backward direction, the degree of ionization, the degree of dissociation of the weak acid, acetic acid, decreases. Like simple, the degree of dissociation of weak acid decreases in presence of common ion, which is produced by the strong electrolyte, and this is called the common ion effect. Now this is the end of this topic. In this class, I am going to discuss the some problems based on the common ion effect. Like, take an example of calculate the degree of dissociation of 0.01 m acetic acid, which is a weak acid, in first in water and the second in 0.1 m aqueous sodium acetate solution. The K value of the acetic acid is given, which is 1.8 multiply 10 raised to the power minus 5. Now take first in water, the dissociation, the degree of dissociation of acetic acid in water. Now already we know the dissociation constant for the weak monobasic acid is K is equal to C alpha square upon 1 minus alpha. Since the acetic acid is a very weak acid, the alpha is almost negligible as compared to 1. That means alpha can be neglected. 1 minus alpha is approximately equal to 1. Now the K is equal to C alpha square and the alpha is equal to under root K upon C. And the K value is given and the concentration of the acetic acid is given, which is 0.01 m. The degree of dissociation of acetic acid in water is about 4.24 multiplied 10 to the power minus 2, which is equal to 4.24%. The degree of dissociation of acetic acid in water. Now in degree of dissociation of acetic acid in 0.1 m sodium acetate solution. Sodium acetate, which is a strong electrolyte, dissociate almost 100% and gives the acetate ion concentration. The acetate ion concentration in this solution increases. Now the concentration of acetic acid is C1 minus alpha. It is at equilibrium concentration. The acetate ion concentration is C alpha and the H plus ion concentration is C alpha. Since the sodium acetate is a strong electrolyte, it ionizes, it dissociated almost 100% and gives 0.1 m acetate ion at equilibrium. 0.1 m acetate ion concentration and the 0.1 m sodium ion concentration. Now the acetate ion concentration in this solution increases and the total acetate ion concentration in this solution is C alpha, which is produced by the acetic acid, and 0.1 m acetate ion concentration, which is produced by the sodium acetate by complete ionization, by almost 100% ionization. The acetate ion concentration in this solution, it becomes C alpha plus 0.1, C alpha plus 0.1, and the concentration of H plus ion in this solution is C alpha and the concentration of acetate ion is C1 minus alpha. Now the K value remains constant, then K is equal to C alpha plus 0.1 multiplies C alpha upon C1 minus alpha. Since alpha for this weak electrolyte, for this acetic acid is very small, that's why C alpha can be neglected as compared to the 0.1. Now this C and this C can be cancelled out. 1.8 multiplied 10 to the power minus 5 is equal to 0.1 alpha, and the alpha, the degree of dissociation of weak acid, acetic acid in this solution, it comes 1.8 multiplied 10 to the power minus 4, which is equal to 1.8 multiplied 10 to the power minus 2%. Then the degree of dissociation of this weak acid, acetic acid in 0.1 m sodium acetate solution is very less as compared to the degree of dissociation of acetic acid in water. Simply, the degree of dissociation of this weak acid, acetic acid decreases in presence of the common ion acetate ion, which is produced by a strong electrolyte sodium acetate. Thank you.